Hello and welcome to SciLux, the podcast where we talk about scientific developments and technological changes in Luxembourg, mostly because, as you know, nowadays we also record episodes with European researchers. But today it's Luxembourg, and this also means that we are proudly powered by Research Luxembourg and recording at the Media Center of the University of Luxembourg. And in today's show, our guest is Citlali Bruce Rosete, who is a PhD student at the Space Systems Engineering Research Group, SPASIS, at S&T. By the way, listeners, do you remember what S&T stands for? You know, go Google, check it out. Don't forget, S&T is an important abbreviation here in Luxembourg, so you should know. I will not tell you right now. University of Luxembourg. Her research interests are miniaturized space systems and space technology development. Citlali, thank you so much for coming today.
My pleasure. Thank you for having me.
I noticed you were smiling when I talked about the S&T. Is that the test? You know, when you start studying at S&T, everybody tests you on what it stands for. Everybody knows that because it's not easy to know, right?
Oh, it's not easy. And when you're presenting at anywhere in the world, you're trying to present S&T and it's always the same issue. So yes, we have a kind of exam at the beginning.
Well, you absolutely have to. I even once was promoting SciLux at RTL, and I did a test to the journalists about all the important scientific abbreviations in Luxembourg. So S&T was there, of course. There was LCSB, there was ESRIC, I think LIST, LIH, LISER, you know, there's quite a few. But I think S&T, the problem mainly is that not all of the words are in the abbreviation. So, you know, just a hint. And now we're not telling what it stands for. Go check it out. But of course, if we have a guest from S&T, one of the subjects S&T looks at is space. So today, without any excitement, obviously, we're talking about space. And we're also meeting because I saw you at a very, very important event here in Luxembourg. Every year, listeners, if you haven't visited it, you absolutely need to. This is the Science Slam, and you won the Science Slam. So once again, congratulations.
Thank you very much.
And it was a really impressive win because basically everybody agreed that you should be the winner, and you were talking about satellites, so we'll be talking about that.
Yes.
So how was, first of all, the experience of Science Slam?
Well, it was a new thing for me because I've done science communication activities before, but this was the first time I did a presentation about my topic to lots of people. The Science Slam is a fun way for everyone to get to know about your research. And so I was very excited to just prepare it. I think the most fun I had was preparing my presentation. That day I was very nervous. It went well in the end, and I had fun with the audience. And yeah, I just had fun the entire time.
But how does it actually happen? Because this is, you know, I'm a science communicator, so I know a little bit also of the theory, right? But if you're a researcher, okay, you have your research, right? You have your very, very serious scientific articles. And then you have to go to the lay audience and you have to show them slices of cheese, as you did, right? Where do you get the gaps? Do you research how others talk about space and satellites, or do you get your ideas yourself? How was it in your case?
In my case, it was a big step, changing from the academic set, or you're always thinking very technically about things and trying to think about it in a way that people will understand and relate to. Is a change you have to make. In my case, I did it myself. In my everyday life, I started looking at stuff, trying to relate it to my satellites. So when I was in the supermarket, I was just walking around and then I saw the cheese aisle and I saw the slices of cheese and they turned out to be the exact same size and shape of my satellite. And I thought, why not? So, that was fun. And then in our lab, we always talk about our other satellite, the size of a Rubik's Cube. I thought, why not actually bringing a Rubik's Cube and showing to people so that they can actually see and relate to it way more than they would normally when they hear the word satellite.
Of course, and this is one of the examples of very good science communication, right? You always have to find an example from real life so people can actually understand the sizes, because we do have problems with sizes in general, right? Also, sometimes when I wonder even what's 10 centimeters or 20, I'm like, okay, I need a ruler. I don't exactly remember what it was. And recently I was actually listening to a podcast where experienced science communicators were making fun because they were exactly explaining how big something was. And the examples they were using was of something extremely obscure. So something that people don't know how big it is, and was really like, I don't know, the walk of these people in the 15th century of something. It's exactly the opposite, of course, because normally you are supposed to give examples that people can relate to. So let's say we're talking satellites, but as you said, slices of cheese and not, could we say normal satellites? First of all, when I say satellite, what is the size you think of? Is there a size of a classic satellite in the vocabulary or not?
Well, typically, no. You have every type and size and shape of satellite. We have the biggest one, the ISS. That's, as I mentioned in the Science Slam, it's about the size of a football field, very big. And the weight is about 3 blue whales, like 450 tons. So that's huge. But then from there, you can go down to any shape and size you want. But if you ask me personally about what I consider a small satellite or the size of a satellite, I will immediately think of tiny satellites, because that's what my PhD is about. So I think of satellites that can fit in my hand, basically.
Before we talk more about those satellites and their sizes, where are they actually? Because that's one of the misconceptions I think people also have, is that it's just one orbit that they go around. But it's not, right?
No, you have many different types of orbits around Earth, and they all serve different purposes. They are for different applications, different types of satellites. What you want to see, what you want to achieve with them is different. So, for example, you have, first of all, low Earth orbit, which is very popular right now. It's the one I work with the most because these very small satellites work primarily in a low Earth orbit. This covers altitudes which are below 2,000 kilometers, and it's a very populated area. As I mentioned, they're used for communications, for Earth observation. This is actually where the International Space Station is located, so our astronauts, that's where they go. And you also have the Hubble Space Telescope, which looks at the universe, and you have amazing pictures from there. That's also in LEO.
And loads of debris, too. I have to mention that too, of course.
Yes, lots of debris. Sustainability is super important right now. And particularly in my field, I'm working with very small satellites and I'm working with lots of them. So it's very important to think about debris and sustainability. And of course, we always take it into account when we are designing our missions.
Okay, so that's low Earth orbit. And you said that's your focus, but let's go off your focus a little bit. What's next after LEO?
All right, so after LEO, we have the medium Earth orbit, which is from 2,000 kilometers to about 36,000 kilometers. And this is where you have, for example, GPS, so also very important for us.
Okay, for example, GPS. And then later on, medium after medium?
After medium Earth orbit, we also have geosynchronous orbit and geostationary orbit. Geostationary orbit is a type of geosynchronous orbit, which is at exactly 35,786 kilometers. And that's a very important number because this orbit is super interesting. It follows the orbital period of Earth, so it rotates at the same rate. This means that if someone were to look up in the sky, they would see the satellite in the same exact position at any time.
That's why geostationary, because you have a feeling that it's not moving, because it's moving together with the Earth.
Yes.
And why is it important? Why do we need a satellite that is all the time in the same spot, if it is there?
They are used a lot for communications also. For example, TV stations. If you have, I'm from Mexico, so if you want a channel in Mexican TV, they usually put their satellites there to always look at the same position, the same countries, the same region, let's say.
And we're talking satellites, and of course we have to mention it. Elephant out of the room, or whatever you say, Elon Musk. Which orbit is it in? Starlink?
Starlink is in low Earth orbit.
As well?
As well.
On top of it. So you said ISS, Hubble, Starlink, all the debris, and all the small satellites.
Yes.
And we are still launching stuff.
Yes, we are still launching.
And there's no space.
Yes, well, that's why we need sustainability, and it's super important to take care of it and to, always comply with regulations, because we do have regulations and it's important to comply with them and to think responsibly about this use of space.
Of course, I even recently heard that there are some plans of designing wooden satellites that would burn better, right?
Yes, I think the first one was launched by Japan last week, and that was very exciting. I want to hear more results about it because it may change some things.
Fingers crossed for that. But coming back, so okay, we have already a picture. Listeners, if you're interested in what is there, you actually even can have like internet maps where we can see all the working and non-working satellites at different orbits. Absolutely, we'll share some links in the show notes. But as we're talking about this crowd of things going on, I think it's a good moment to ask the pub quiz question, because you prepared something about exactly, how many of those we're talking about here. Remember, we're focusing only on the small satellites, right? So remember the question as usual in the beginning of the podcast and the answer only at the end. So if you can ask the question, and then we will reveal the answer at the end.
So like you mentioned, I love small satellites. And so my question is, how many CubeSats and then how many Pocket Cubes have been launched to space? And I think we'll talk about them a bit later to explain to you what they are. And then we'll see how many have been actually launched.
Exactly. So we will know how many at the end, but now we have to exactly define them, because we didn't do that. We just defined the orbits, but we didn't define the small satellites. So what is the biggest size of a small satellite? Is that the CubeSat then?
Yes, a CubeSat is a small satellite. So you can consider it, or I consider at least a CubeSat my upper limit when I talk about size. And from there you go down to however small you want. So if a CubeSat is a cube that is 10 by 10 by 10 centimeters edge, its weight can be less than 2 kilograms, then I go down to a Pocket Cube. A Pocket Cube is a cube also, and the edge size is 5 centimeters.
So it's half, basically.
It's actually 1/8. So it's very impressive how small it can be. And if you ever have a Rubik's Cube, that's exactly the size of 1P Pocket Cube, as we call it. And from there, you can go even further down to what we call chipsats. A chipsat is a PCB, so a printed circuit board, which is 5 centimeters edge on average. So it can go, from maybe 7 centimeters down to even 3.5 centimeters.
That's really tiny.
It's very small. It's actually the smallest satellite ever in orbit. It was developed in the University of Cornell, and the size is 3.5 times 3.5 centimeters. The weight is, I think, 5 grams. And it's very impressive that you can get to that size and still get some data, and you get it down on Earth, and it's really cool.
But why so small?
Well, yes, that's a very good question. And it's a question I get from many people when I tell them, hey, I work with very small satellites. And they say, okay, cool. But then what do you actually do with them? So when we talk about CubeSats, which is already very small, you actually still talk about the cost being in the hundreds of thousands of dollars, around that. And then the development can take up to years. So when you talk about universities or high schools or even startups wanting to work on satellites to get introduced to this world, it's still quite difficult for them. And if you want to develop more than one, then it's even more difficult. So one way to reduce how difficult this may be, or to enter space easier, would be to reduce the size. What you do when you reduce the size is you reduce the number of components, you reduce the complexity or the interactions between these components. You also need less people to work on the project. It takes less development time, and the launch costs are reduced. This means you can send a lot of them together at the same time, and this ends up being what I work with, which is swarms of satellites.
And swarm is an important word in space in general, because you also have like swarm of rovers, right? So you try to work on systems of robots or systems of satellites in this case. But then, wait a second, if you need swarms, it actually means you need to launch many of them. So in the end, you come up with the same cost or not, or I'm not getting anything.
So when it comes to the cost per unit, for sure it's lower. So if you want to develop one CubeSat, it's going to cost hundreds of thousands of dollars. If you want to develop one Pocket Cube, for sure the cost is lower. It's in the order of maybe tens of thousands of dollars. So that in itself helps these teams from universities, from high schools, from startups to develop their own satellite. You don't need to develop one full CubeSat. You want to develop just one Pocket Cube. That's what makes this door to space more open for them. When it comes to cost per mass, for sure it's going to be the same as all the other satellites. But you're talking about a smaller satellite, and launching one of these satellites is smaller.
Okay, so it makes sense. It's not only the cost of the launch, but also the cost of development.
Exactly.
How do you launch such small satellites? you need to launch them on something, right?
Exactly.
You don't launch them on their own.
No. So how you do it is the same way you do it with CubeSats. So when you launch a normal satellite, you usually have some empty space, dead space in your launcher. And this you use to do what we call piggyback on that satellite. So now we do that with CubeSats, and we also do it actually with Pocket Cubes. So you have other empty spaces where you put the launchers or the deployers for the Pocket Cubes. And you can also do deployers for chipsets the same way. So once you are in space, you launch your satellite and you can do piggyback on the piggyback. And then you launch your very small satellites.
Wait, but it's piggy.
Piggy.
Really,
yes.
like a pig, like the animal.
Yes.
Okay. I just wanted to make sure I got it right. Because it sounded cute, but I was not sure. Now I'm 100% sure. So it's basically this kind of idea of putting them together and using the dead space, as you said, which means basically that it's like hitchhiking. It's for free, more or less. You have to pay still, but still cheaper than other thing. What remains is that a CubeSat on its own, is it easier for it to fly around or more difficult? You know, I mean, how do you get a deployer, you put it on an orbit, and I would assume that if something is bigger, it's gonna be easier for it to revolve around the Earth than if it's these tiny little pocket cubes. Am I right or not?
Well, what is more difficult is controlling the satellite because it's smaller. So you definitely have more limited capabilities on control because there are very limited propulsion options right now for Pocket Cubes. You also have limited area. So if you want to control it using, for example, drag, atmosphere drag, it's a bit more difficult maybe than with larger satellites. But you can still do lots of things with them.
What's the propulsion for Pocket Cubes?
It's mainly for controlling the orbit. You can also use it maybe for controlling altitude, but we use it mostly for orbit. It's very important. As we mentioned, decay times in low Earth orbit are very important to bring the satellite down when we want so that we comply with the regulations.
So you mean to burn it once the life is over?
Exactly. So we have a limit of 5 years when we are in low Earth orbit, and we make sure that we bring down the satellite within those 5 years so that it burns up in the atmosphere.
Okay, lay perspective. I am thinking of a propulsion system. It's, obviously the first thing I can think of. If something is flying around the Earth, it's a rocket type of thing. So I imagine this tiny little pocket cube with, like small engine type of, how do you call it even, fire going out of it. That's not the case. Or is it? What's the system? What's the engine there?
Well, you have many different ones nowadays. For Pocket Cubes, we have some that use liquid propellant. So that's a thruster. And yeah, you do have a little bit.
You really have a tiny thruster there.
Yes.
Oh, that's so cool.
It's very cool. Still hasn't been tested in space, but we hope to get there. This is a very new field, so we are still learning. But hopefully we will get there because then we'll have the control that we want.
Okay, so what is there that we are sure of? What has been tested so far with Pocket Cubes? We will move to ChipSat in a second.
For Pocket Cubes, you do have some deployable solar panels, which is very important because being so small, you have limited area to put your solar panels. And so therefore, the power you have to make your satellite work is also very limited compared to larger satellites. So having deployable solar panels is very important. That has been done. It's been done a lot. We also can communicate with them. So the communication system is now proven by many people. We actually have built our own Pocket Cube at SNT with my research group, the Space Systems Engineering Research Group. It's called POQUITO. And what we want to test there is an ADCS system because right now there's not many ADCS systems. So attitude control
Exactly,
systems.
thank you.
Yeah, sorry. There's not many attitude control systems for Pocket Cubes yet. And we designed our own within our group and we want to test it. And yeah, we're building a platform and then we can put many different payloads there to test different components.
And what happens if a Pocket Cube crashes into a piece of old satellites or debris? That's it? Or can you actually, because you're talking about altitude control, are you also able to actually avoid, or this is not yet discussed or planned?
When we want to get the license for the satellite, we actually have to make a study of whether or not we will hit any satellites. And we have to make sure that there's 0% probability that we will hit one of these satellites. Because yes, we have attitude control, but we don't have orbit control. And to avoid any other satellite, you use the orbit control system, so propulsion. We don't have propulsion in POQUITO, so we do have to make sure that at the orbit where we will be released, we will not hit any other satellite to damage it.
And you can know that when you plan the mission?
Yes, that's part of the calculations we have to make. So there are softwares, special softwares, where you have databases with every satellite that is active or not active, but that is there in orbit. So you can track all these pieces of satellites, and then you have to make sure, using these databases, that you will not hit any of them.
But then I don't get something. Sometimes it does happen that certain objects crash into each other, or even bigger satellites crash into debris. They didn't do the calculations?
That's a very good question.
And you leave it there, I assume.
I think so.
Okay, fair enough. Just wondering. So we have the pocket cubes and we have POQUITO. I understand. And then, of course, if you already have it, you have to find a place where you can send it, right? So what's the plan? What nation like Luxembourg and SNT, what can you do with a pocket cube? Do you have providers of, I don't know, where you can send your pocket cube with, or you pay them for the trip, or is there something open for the researchers? How does it work later on?
I think you have many options, but right now the option we used, at least for POQUITO, was going through a deployer. So we have a contract with a company called Alba Orbital in Scotland, and they put our satellite inside their deployer. And then they are inside Italy's D-Orbit system, which will take us to orbit. And from there we will be deployed. And all of this will go then into the SpaceX launcher. So, there's many people involved and many different layers to this. And that's why I mentioned the piggyback on the piggyback.
Exactly. It makes me think of, a plankton, and then some fish, and then some whale, and then some bigger whale.
Exactly.
Else, more or less. More or less like that. Okay, because you were talking about, 3 blue whales size of the ISS, and somehow I went into deep ocean to think about satellites. Okay, so these are pocket cubes. And you mentioned that your PhD is also related to that.
Yes.
So it's the altitude control system, you said, or not exactly. What are you working on in your PhD?
So in my PhD, I'm doing mission design and mission analysis for pocket cube missions in general. I'm focusing on the mission analysis mostly, which is orbital dynamics, how the satellites move. And I work with swarms of pocket cubes. As I mentioned, yes, we are sending right now one satellite, but that is to test the systems to see whether the components work or not. But the idea is that in the end, we can send swarms of them, so many of them together to achieve a mission. And in my case, I'm focusing on what is called distributed beamforming. That's what my PhD is about.
Exactly. And I'm smiling because this is one of the buzzwords I've noticed when you were writing. I think one of the articles, I don't know where I found it, but I did find beamforming and I have no idea what it is. So tell me, please.
Yes. So the idea is when you have one antenna, if you want a more directed beam or your signal to be more directed, you have to make the antenna larger. And also if you want to direct your beam at a certain location, you have to physically move your antenna to that position or angle. What beamforming is a technique where you use an array of antennas, so multiple antennas, and you combine them so that at certain points the signal is destroyed or you lose the signal, and then in others it's constructively interfering, so then you have the beam in that direction. And that way you don't have to physically move the antennas and you don't have the limit of space. So when we talk about satellites, there are satellites doing beamforming, but they have limited space because of how big they are. So whenever you reach this limit of how big the satellite is, so how big the antenna can be, then you can move to these many antennas, these distributed arrays of antennas. And their swarms are very interesting because also in one single satellite, you have limited space, so limited distance between these antennas in the array. When you want to move further than that and have greater distances between them, you can use a swarm of satellites and then you have even larger antennas.
Yes, but the satellites are small.
Yes, exactly.
And doesn't it mean that the beam is then less potent because of that?
No, this will be very technical if I try to get into it. So when you work with an array of antennas, you don't really change the power of the array or the signal. And what you do is you direct it more, and as you direct it more, then the power is, let's say, better directed. So you do have limited power in your satellite, and the size of the antenna will also affect the frequencies you work with, but that will not affect how potent this beam will be.
Okay, thank you for trying to explain to me something that is very technical and complicated, because I got it.
Okay, good.
So, this is good news. Okay, so swarms and planning the mission. So is it all about calculation then? What is, in your case, mission planning? Is it really like, running algorithms to understand the angles, or what is it about?
There are many different parts of the mission design. So one part of it is definitely all these calculations that you have to make. But before that comes actually what you want to achieve. So you have to define your science case, your science questions, what you want to solve with your mission. And once you have that, what you want to achieve for your mission will give you the requirements for your system. And so when you have your requirements comes the fun part of coming up with ideas. And with your team, you discuss a lot and you see what would work, what could not work. And after that, for sure, you have to do lots of calculations because you have to corroborate that these ideas will work or not. So then these calculations, you do them for each subsystem. We've been talking about propulsion, about attitude control. You also have to make sure your communications is correct so that you can send all the data you generate back to Earth. You have to make sure that your solar panels will give you the necessary power for your system. You even have to make sure thermal-wise that you don't have any part burning up or any part just cooling, freezing, So that is super important. You also need to make sure, as I do with my PhD, that the trajectory is okay, that the orbits are okay, that you don't hit anything, that you will get wherever you want to go.
And if it doesn't work out, then you fail your PhD? The testing phase is one thing, but then the real mission is another thing. But I guess that's not related, right?
Definitely. No, I hope not. No, but during the mission design, there are different ways to approach it. So, for example, I've been involved in 2 different types of mission design. One for a very big satellite, traditional sized satellite. In that case, the mission design goes through first the preliminary design of the mission concept, and then you do concurrent engineering, concurrent design to do several iterations on the engineering on these numbers that we calculate to get to the most efficient solution. Then you have the approach with very small satellites, which we used for POQUITO. It's such a small satellite, you cannot really approach it in the same way. You have a different way to design it, and that is a very iterative process. So the first one was kind of linear. The second one is very iterative. So you try something out, test it, doesn't work, you go back, try, test something else, and so on. That makes it faster in the end. But of course, with a larger satellite, you cannot do that because it's very expensive. So you have to make sure from the design that you're sure of what you want, what you will do. So there are many different ways to approach it. It depends on the satellite and on the mission.
And when you talk testing, is it like simulation, computer simulations, or is it actually testing in some analog environment?
Both, definitely. When you do lots of simulations, that's necessary for the trajectory to see which orbits you are in, to see whether your transfer orbits are correct, whether you will be in the orbit you want and for how long and how many maneuvers you need to maintain that orbit. Super important. And you also need, for example, POQUITO again. We need to test all the components beforehand. So you do this analog satellite down here in our labs, and you have to test all the components to make sure your circuits are working correctly.
So you talk about maneuvers. I started thinking, we're talking all the time about smaller and smaller satellites. So what is it that we are actually miniaturizing? Is it the chips themselves, or is it also the propulsion as we're talking, or the ability for the satellite to move? What is possible to be miniaturized?
It's definitely the systems. So it's the same as a cell phone. Before we had very big telephones, and slowly the components for the telephone were smaller, so we were able to build smaller telephones. With the satellites, it's exactly the same thing. So now we have very small components, and we're able to make a working satellite with these very small components.
Because I haven't really seen those small satellites moving around. I've seen a CubeSat. I haven't seen smaller ones, especially in motion. I don't know, I just keep thinking of, like wing-like thing, or I don't know, small. My imagination is not letting me imagine it the right way. That's why I'm asking probably stupid question.
No, it's okay. I would say to imagine it the same way as a CubeSat, actually, because they move the same way. Maybe because you don't have as much control, then they tumble more. So they are rotating more than a CubeSat, which you can control the attitude of. But in general, I would say it's kind of the same as a CubeSat. As I mentioned, everything is limited. Also, propulsion is limited. So maybe you wouldn't be able to control the orbit as nicely as a larger satellite.
Okay, clear now. Yay.
Good.
Another thing I was wondering is that if we're talking about swarms of those, then I guess there is also a lot of pressure on how they are deployed, because they have to be deployed so they form an array. Right? Are we there technologically? Is it possible for the deployer to kind of provide you with, we will put your pocket cubes exactly in the place you want?
There are definitely studies on how to deploy satellites such that you get this formation flying that they call. I don't know that they've tried it in space with these very small satellites. But what some of us are doing, and that's what I'm doing in my PhD, I'm studying how to work with them without that control. So with my PhD, I do have to maintain them within a certain bubble to keep this antenna array as big as I want and not larger. But I don't need them to be equally spaced between them, which is super cool. And it's an advantage, to them, because we can avoid that control.
Of course. Another thing what they're doing, what is so important, is obviously all the data that they gather. And I was wondering, is it possible for them to already analyze the data that they get while being in orbit? Or are we still working on technologies that first send the data to us and then we have to process it?
Given the size of the pocket cubes, definitely the second one. So it's very small and still the computational capabilities are very limited. So what we're thinking about, and it is usually done, is having this relay satellite. I call it chief deputy. So the deputies is your swarm, and then the chief would be this mother satellite to which all the satellites send the information, and then from there we can communicate with Earth. But there's, of course, many different configurations that you can use. Definitely not the only one to have this parent satellite there. But indeed, with the capabilities of pocket cubes right now, it's very hard for them to do the computations themselves. Maybe with larger pocket cubes, it would be a bit easier, but mostly we are sending it back to Earth.
But it is a kind of a soft spot, isn't it? I mean, because you consume energy after all in order to send all the data. So if it was possible to just have one pocket cube that analyzes and then chooses whatever you need and then sends it over, and maybe also less data is actually sent, that would be a good idea, right?
Definitely.
But that's something that has to be still developed.
Yes, there are lots of studies on it for sure, but for now, we are not considering it as an option.
Okay, we talked pocket cubes, so I think the only thing remaining are the chipsats. So first of all, of course, why make it even smaller?
Why not? I mean, chipsats are very cool.
I can see you really like your job.
It's, again, the same case as with pocket cubes, because maybe they will open different types of missions that you can achieve than the other satellites. So with chipsats, for example, the first thing that comes to my mind is you could release a cloud of chipsats to study the aurora. Because right now, satellites, some of them do study the aurora, but when you do have this very intense aurora, it would be very nice to get measurements of it at that time. And so what you can do with chipsats being so cheap, because they're so small, it's that you can do these opportunistic releases. And so whenever you know that there's going to be this very intense aurora, you could send a cloud of these satellites and then do the measurements you need, send them back to Earth. And then because it's a very low Earth orbit, they immediately re-enter the atmosphere, burn up, and then that's it. So you don't have debris in that case, and you get your measurements. So it's a very interesting application, and I think that's why it's worth considering these very small satellites, just because they could open different types of applications than the ones we currently are able to achieve.
And it's a field that is even less developed than pocket cubes.
Yes,
So you said it's been like one that has been launched?
There's been several that have been launched, actually, but not that many. Also because it's very hard to track them because they're so small. And again, thinking about sustainability, about regulations, we have to be careful with that. So in the group, we developed POQUITO. We have also developed the chipset, and we have put the chipset on top of POQUITO so that at every time we know where it is. It's an independent satellite. It's connected mechanically, but we will know where it is at every time. We can track it.
And it doesn't have a name, the chipset?
Not really. It's called chipset 2 because it's a second version. Yeah, I'm sorry to say, but I think in the future we might think of another name for it.
Okay, yeah, because POQUITO is such a nice name, so I was hoping that there'll be something more, journalist, sorry. Okay, so now it's attached, but the idea is that at certain moment you would also just launch it somewhere.
Exactly. When tracking capabilities advance and then we're able to track even smaller objects, then we could send these satellites.
And how are they tracked right now? So you're saying the capabilities are not such. So for pocket cubes, for example, how do you track pocket cubes?
It's usually done either optically, so through telescopes, or I know radar as well is used. And yeah, the resolution that you need is minimum 10 centimeters to be able to track it. In our case, the antenna is longer than 10 centimeters, which is how you can track it. That's very important to take into account. And it's why you cannot send something smaller than that, in theory. Yes, yet.
But for the regulations, how does it work? Do you have to also register those, just like any other satellite? Any kind of launch has to be registered?
Definitely, yes. And it was a very lengthy process for us. I think half of the work, or a bit more than half of the work, was preparing paperwork for the licensing. And it was a lot of work, but in the end we got it because we were able to make sure that, first of all, we can track it and that the decay time is less than 5 years, actually less than 3. So very, very important work.
The comparison of how much time it takes to get all the paperwork done and how much time you actually get to fly it in space is probably not the best. I don't know.
Yes, but definitely necessary. And I think it's important to do all the work to comply with the regulations.
And do you think, as we're talking sustainability as well, these small satellites could also help us with cleaning the orbits or not really? I'm just kind of throwing it out there.
That's a very good question. And I don't know if in the future maybe they could be useful in some way. Maybe some missions where you have tethered satellites and a type of web between them. I don't know, I'm just rambling here, but, maybe in the future when we have the technology better developed, for sure. But for now, we're just careful to bring them down as soon as we can.
And that's already good, for sure. And also important because it's not that there are only 2 pocket cubes that have been launched, as far as I know. And this leads me to the pop quiz question, of course. So listeners, remember, Citlali asked a question in the beginning. And now, of course, the request to you is to repeat the question, please, and then tell us the answer.
The question was, how many CubeSats and how many pocket cubes have been launched to space? I can tell you as of May 2024, 2,396 CubeSats were launched and 83 pocket cubes. And I can tell you soon also Luxembourg will have its first pocket cube in space because we're expecting to launch POQUITO in January 2025.
So I can't wait for that. You need to totally tell me. I mean, I probably will see in the news anyway, but, I'll be keeping my fingers crossed for that. And brilliant, we're talking right now. So just before it gets launched, are you going to be present there for the launch? I guess not, right?
I guess not. But definitely watching it with the whole team and an afterwards party will be due.
Absolutely. You deserve it for sure. And I just realized that, we talked about the size of the CubeSat. We talked about the size of the pocket cube. And then somehow I just said chipsat and I didn't ask you. So how small is a chipsat actually?
The chipsat can be as small as 3 times 3 centimeters and only a few millimeters width. So it's very, very small. And in terms of weight, down to even 4 or 5 grams. So that's why I took the slice of cheese to compare it, because I like to think now that every time I'm eating a sandwich, I have the model of a satellite right there. I'm eating it. That gives you an idea of how small.
Yes, exactly. But at the same time, this really means that there's only one chip.
Yes, exactly.
So obviously it can't really process all the data and do analysis and whatever. I mean, it's different. But then the idea, as you said, a cloud of chipsets makes sense as well, because you can imagine that it kind of creates that kind of a swarm or cloud of things for sure. Okay, very interesting. Thank you, Citlali, so much for sharing this with us. And listeners, remember that if you want to know something more about CubeSats that we didn't really discuss that much today, there was an interview that I did a couple of years ago already with Dr. Jan Thumel at SNT as well. We were talking about CubeSats and what SNT did actually, because a lot has changed since then, but still you can check that out. And what remains is to thank you so much for coming today, and good luck with the launch and good luck with your PhD.
Thank you very much, Hannah, and thank you for having me, and to the audience for listening.
And this is it for today. Don't forget to subscribe, to follow us, to write to us. Of course, go check out our website, scilax.eu. We are present on all major podcasting platforms and always open for your suggestions. And of course, I have to say that as well. There's this green support button on the website. And if you click it, then, you can just show your support and let us develop even further, go to Europe, talk to European scientists, and support Luxembourgish science as well. Thank you so much. This was Scilax, and my name is Hanna Siemaszko.